Hi guys, this is A plus tutoring, and in today's session I have a session with a student on the physical properties of organic compounds. But then the first part of our session wasn't recorded, so I'm gonna record it solo. And then the session with the student will come in after a bit of a while. I also came across questions from students who were asking if I do record all my online one-on-one sessions, since my videos are session with the students. And no, I do not record our online one-on-one session. I'm recording this session because it is with a family member who agreed for me to record our session and to use them for my YouTube videos. But if I'm to have a session with a student, a one-on-one session, I do not record our session unless if you'd like me to record it and send it to you for maybe later use. Okay, so we'll be doing with the physical properties of organic compounds. So what we have boiling point, melting point, and vapor pressure. Boiling point, it's when a liquid changes to a gas, right? But how we define it as it is the temperature at which the vapor pressure of a liquid is equal to the atmospheric pressure. And now melting point is the temperature at which a solid melts to be a liquid, right? And then we now have this vapor pressure. Vapor pressure, we consider it, let's say, the ability of a compound to change to a vapor, or we can say it's free will to change to a vapor, for example. So once you have a low vapor pressure, it means that my vapor pressure is inversely proportional to boiling point. So once I have low vapor pressure, it means that I have high boiling point, meaning that this compound is not readily willing to change to be a vapor. Let me put my laptop on charger. So once you have a high vapor pressure, you know that compound is willing to change to a vapor. That molecule is willing to change to a vapor, so it would have a low boiling point and a low melting point. Okay, so they're inversely, vapor pressure and boiling point are inversely proportional to that. Okay. And then now we have intermolecular forces. So the intermolecular forces, we have the London forces, and then we have the dipole forces and the hydrogen bonding. So the London forces are mostly between our alkenes, and alkynes, while our dipole are now between our aldehydes, our esters, the ketones, anything else that has the O, right? While hydrogen bonding is only in between an OH, and the only time we have an OH is when we have what? An alcohol, right? As well as a carboxylic acid. Right. So these are now, the alkanes, alkynes are our London forces, and then aldehydes, esters, ketones are our dipole, and then the alcohol and carboxylic go on hydrogen bonding. Okay. So once we have weak intermolecular forces, so we know that in between the three, our London forces are weaker, and then the next one is the dipole, and then the strongest is the hydrogen bonding. So when you have a weak intermolecular forces, it means that I need less energy to break that bond, right? So once I need less energy to break that molecule apart, that would mean that I have low boiling point and low melting point. It is quickly gonna turn into my liquid, turn into my vapor, meaning I will have a high vapor pressure. Because remember, once it's quickly gonna turn into the vapor, it means that it's readily, meaning it has high vapor pressure. Once I have now the strong intermolecular forces, I now need more energy to break those bonds, meaning I'm gonna have high boiling point and low vapor pressure. And then remember, we said that our alkanes, alkenes, alkynes, and then haloalkane. I'd forgotten the haloalkanes when I was listing them up there. But then we now have our haloalkanes and esters, ketones, and aldehydes. They have what? Weaker intermolecular forces. Why? Because these ones, they fall under the induced dipole-dipole and the dipole-dipole, the London forces and the dipole-dipole, right? But if we were to compare, let's say for example, you are comparing the London and the dipole-dipole, right? This is our London and this is our dipole. The dipole would actually be stronger than the London, meaning these would have a higher boiling point compared to that one. But if we're comparing everything, then this one will have the highest, then we go to the middle one, and then the lowest, if we're to compare everything. So our London have the lowest, meaning they need the less energy, the least energy to break, and making it low, right? And remember, once boiling point and melting point are low, our vapor pressure is high. So once you have strong intermolecular forces, you have your higher boiling points. So this ones, it's when we define the intermolecular forces using our functional groups, right? So we are now going to move to where we now define the intermolecular forces using maybe compounds in the same functional group. For example, if I'm to be comparing compounds that are all alkanes, how now do I compare and say this one has more stronger forces than this one, when I know that all of them have what? A London force. Now that is where we'll be going to. Okay, so if they are to be in the same group, there is one with a shorter chain, and then there's going to be one with a longer chain. For example, I have an alkane, and then I have the 3-seed alkane, right? And then I have this one. Do you see? Because this one is longer, I'm gonna need more energy, because obviously the energy I'll have to break here, here, and here. I'm just breaking maybe 2 or 3 bonds, right? Here I'm gonna break 1, 2, 3, 4. I keep going on and on. So I need more energy here than I need here. And therefore, that's when you'd say, good, okay, so a shorter has weaker forces, and then we'll have a lower boiling point than the longer. A longer will have more forces. Why? Because there are more bonds that are needed to be broken. Okay. And then now we move to branched, right? Molecular forces, molecules that are branched. For example, we still have our alkanes, right? I have this alkane. It has my what? 5 carbons, but 5 is the longest chain. And then now I have that. Do you see now that 4 is the longest chain, and I have a branch, but they'll have the same number of C's and same number of H, just that this one is branched and that one is a straight molecule. So now the branched one has weaker intermolecular forces. Why? Because I would compare this to being your leg, for example. Let's say that's your leg, and then that part is your heart. Why? Because it's inside you. So it's gonna be harder to break the bones that are inside. It's harder for me to take your heart than it is for me to just cut off your leg. It would need a whole complicated surgery for me to open up and get your organs than it would need for me to just cut off your leg. So your leg acts as the branch, and then the longer chain is now your organs. So you see that you need more energy to get any of your inside organs than you'd need to cut off a leg or an arm. That's where I'll now say that, so that would mean that molecules where the carbon chain are branched, they have weaker intermolecular forces, meaning less energy to break the bonds, and then less energy for molecules to evaporate, meaning high vapor pressure, and our low boiling point and low melting point. So now the straight chains will now have more energy and a higher boiling point and a lower vapor pressure. So I think for the video that I did with the student, this is where it started recording. So the continuation from this onwards will be with the session with the student, where we'll now do examples on which one is more vapor pressure, which one is more melting point, and which one is more stronger than the other. So the fact that this one has a shorter chain and this is longer, that means that I need less energy to break these bones here, but I'll need slightly more energy to break these ones.
But at the end of the day, they're both still weak.
They're both still weak, but now if you're to be comparing these two, this one needs more than this.
Yeah.
That's why they say that a shortened carbon chain will be weaker, while a longer is stronger, because you're comparing just these two.
Okay.
But if you're comparing them against an alcohol or a carboxylic acid, they're weaker than those two.
Okay.
Okay. So I think we can go to the question now. Okay, and then there's this where it says that molecules where carbon chains are branched, right? Like, you see I have a branch, right? Compared to, okay,
wait, so is the one on top weaker because it does not have like a longer chain as well?
yes.
Okay.
So it's easy to remove this branch than it is to remove part of, because let's compare it, for example, with this is your leg, right? And then this is your heart. It's
gonna be,
yes, it's easy for me to cut off your leg than it is for me to reach in and take your heart, because it's part of you. So now let's try this question. Okay, so it says 3.2, describe the trend in their boiling points. Describe the trend in the boiling points. Here are the boiling points.
higher the relative molecular mass, the higher the boiling point will be.
Yes.
Then the lower the, what is it, the relative molecular mass, the lower the boiling point, like that.
Yes, they wanted what? Boiling points of the 4 alkanes, right?
Alkanes, the single bonds.
Yes, the single bonds. So now we now go back and we now check to which ones are alkanes. They tell us that this was alkanes being compared with alcohols, right? Meaning we know that this one, it's an alkane, this one, it's an alkane, that's in that, right?
Alkane, alcohol.
Okay, so now let's see. This was 30, while this was minus 89. And then we went to a 44, this become minus 42. So this one increasing, that one is also increasing, right? Now that's where they now say that you need to explain it. How are you going to explain it? Remember that the higher the molecular mass means that I'm just adding elements. For example, I started with the CH3, meaning it's this one. Right? And then I went to CH3, CH2, CH3, which is meaning I now have 3 C's. Do you see that my chain size is increasing?
It's CC, with the one CCC. Oh yeah.
So now you're just explaining that what we did in the last one where we were talking of the longer chain and the shorter chain. Now you're just explaining that since this is a shorter chain, it's much easier to break than a longer chain. That's what they said by fully explaining the trend in 3.2.1. You're now just explaining that the reason why the boiling point is going high is because the more bonds I have, the more energy I need to break those bonds.
Oh.
Since I'm having more and more chains than before, so I'm going to need more energy to actually be able to break those bonds.
Okay.
Okay. So now,
But what are the points that they specifically need? Is it like, so do I talk about the chains? Chains.
in this case, remember we are comparing things that are in the same functional group, right? So since we are comparing things that are in the same functional group, we are gonna need to compare the chains.
Okay, yeah.
It's the same as if we were to be comparing the alcohols. They're all in the same functional group. Yes, they all have the strong hydrogen bond, but now we are comparing on the size of the alcohol. The greater the size, the more energy we're going to need to break it. For example, if I was to give you firewood to break, right? I give you this size of firewood, I'm like, break it, and then I give you another size of firewood to break, which is gonna take more energy and more time.
The second one.
The second one. It's the same with these compounds. The first ones were smaller, it's these ones, meaning it needs less energy, and then the bigger it goes, it now needs more.
Okay. So the longer the thing, the more energy is required to break it down.
Yes.
Okay.
Okay. And then now we have the boiling point of each alcohol is much higher than that of an alkane. Now, comparable relative molecular mass. Explain this observation by referring to the type and the strength of the intermolecular forces in alkanes and alcohols. Right?
Yeah, which one? Yeah. So what's the types of force in alcohols? Is it London?
No, remember we say that for alcohols we have an OH, right?
Yeah.
And OH is what?
It's not. Oh, is it hydrogen?
Yes, it's a hydrogen bond, meaning it's strong. But then between alkanes we have our London forces. We have our London and our dipole, right? So meaning they are weaker, right?
Yeah.
So that's what we need to explain when we now get to this point, that okay, so when they say that the boiling point of each alcohol is much higher than that of an alkane of comparable relative molecular mass, right? They mean, for example, here this one of 72 and 72, if you're to draw them, we have 1, 2, 3, 4, 5 carbons, right? And
Yeah.
here we also have 1, 2, 3, 4, 5 carbons. So in a way they are similar. The only thing different is that this one has a hydrogen where this one will have an OH, right? So now they are like, okay, why is it that the boiling points are not the same, even though when it comes to their mass they are less close to each other? But why is it that the boiling points are now much like they have a greater difference?
Because the OH is a hydrogen bond, which is a very strong bond that requires a lot of energy to be broken out.
Yes.
Rather than the one that's a London dispersion force, which has forces that hold molecules together. So now it's gonna require less energy for the molecule to break down.
Okay.
So that's my 2 marks.
Yeah.